Welcome back, everyone. I am absolutely thrilled you're here for today's explainer because we are unpacking something truly, literally mind-bending. We're going to look at a hidden structural pattern, a universal data reduction principle that has been independently discovered across 5 vastly different scientific fields. So get ready because we are connecting the very fabric of physical reality directly to the neurons firing in your head right now.
Okay, let's dive right into this. What do a black hole, a mouse's brain, and Demis Hassabis' Nobel-winning artificial intelligence possibly have in common? I mean, on the surface, absolutely nothing, right? But as we act as scientific detectives today, we're going to uncover a shared, hidden architecture beneath every single one of them.
To do that, we have a clear roadmap. 1. Gravity as a hologram. 2. The machine learning bottleneck. 3. Sculpting the biological brain. 4. A learnable universe. And 5. The grand synthesis. This agenda is going to guide us safely through the intellectual wilderness.
But before we really get going, we need to understand the core concept driving this entire explainer, and that's something called a low-rank manifold. Simply put, it's a compressed representation of a high-dimensional space. Think of the universe as a master sculptor. You start with this massive, dense, high-dimensional block of stone, just full of excess, noisy information. The universe systematically chips away and forgets what doesn't matter, carving out a sleek, lower-dimensional structure that retains only the essential physics.
All right, Section 1. Gravity as a hologram.
Back in 1997, physicist Juan Maldacena proposed this absolutely incredible duality. On one side, you have what's called the bulk reality. Think of it as a dense 3D space containing all this complex gravitational physics inside an ADS space. But Maldacena showed that all of that complex bulk physics can be entirely encoded on a lower dimensional boundary field. That's a sparse 2D conformal field theory with literally no gravity at all. It is fundamental dimensionality reduction. A huge number of microscopic degrees of freedom on the boundary efficiently encode classical geometry in the bulk.
And it goes even deeper. Physicist Brian Swingle showed using Mira tensor networks, which map quantum entanglement, that the holographic radial direction is literally a scale of coarse graining. Taking it a step further, Eric Verlinde's work on entropic gravity suggests that dark matter might just be deviations in gravitational laws caused by the entropy or the information of the universe. The massive takeaway here is that space-time and gravity might not be the foundational canvas of reality, but rather the output of an information compression process.
Which brings us to Section 2, the machine learning bottleneck.
So AI engineers actually stumbled onto the exact same mechanism. In 2006, AI pioneer Geoff Hinton published a landmark paper in Science. He took images of handwritten digits, specifically the MNIST dataset, and each of these images is 784 pixels. That's 784 dimensions of data. He ran them through a deep autoencoder, which is a neural network specifically designed to squeeze information down. And he compressed those 784 pixels into a central code layer consisting of just 30 core numbers. Just 30!
The absolutely crucial point here is how well this forced bottleneck actually performs. When you compare the average squared reconstruction error to rebuild the original image, standard principal component analysis, the old traditional way of doing things, had an error of 13.87. But Hinton's deep autoencoder, it blew it out of the water with an error of just 3.00. By forcing the data through a tight bottleneck, the network learned the essential features, and it did all this using about 20 million weights, which, to put that into perspective, Hinton noted is roughly equivalent to just 2% of a cubic millimeter of actual biological cortex.
Section 3. Sculpting the biological brain.
Now, what's really interesting here is how we can map this artificial bottleneck directly to actual biological tissue. In a massive 2026 discovery by Vargas Barroso and the ISDA group, researchers mapped over 7,000 potential connections in the mouse hippocampus. At postnatal day 8, the brain begins with these dense, near-random connections. By day 25, experience-dependent pruning is fully underway, and by day 50, it has completely sculpted itself into a highly sparse structured memory circuit.
You see, the neonatal CA3 circuit in the hippocampus starts totally full. In fact, it's so dense that any single synaptic event is enough to trigger a spike. It's a dense, high-dimensional mess. But the adult CA3 is streamlined. It requires spatial summation from several inputs just to fire. And why does it do this? Well, biological simulations show this pruned, compressed configuration actually maximizes pattern storage capacity. Biology overparameterizes at birth and then runs a long pruning routine to compress down to only what matters. Moving right along to Section 4, a learnable universe.
10 to the power of 170. This is a staggering number. It represents the possible board positions in the ancient game of Go. That is vastly, vastly larger than the number of atoms in the entire observable universe. You cannot brute force a search space this large. There's just no way. Yet Google DeepMind's AlphaGo mastered it. How? Because neural models don't calculate every single possibility. Instead, they intuitively compress the intractable complexity to find the underlying, relevant patterns.
And this brings us to a really beautiful quote from Demis Hassabis during his Nobel Prize lecture. He noted how AI extracts structure from nature, saying, "Perhaps there is some kind of lower dimensional manifold that can be learned. That's maybe true of most of reality." Hassabis is conjecturing that evolution, cosmology, and the physical world inherently produce systems with compressible regularities. Basically, nature is learnable because nature is compressible.
And we actually have empirical proof of this happening right now inside Blackbox AI. A massive preprint study by Kaushik looked at over 1,100 deep networks trained completely independently from one another. This included 500 Mistral 7B language models and 500 vision transformers. And the researchers found that these models systematically collapse into the exact same universal weight subspace. The vast majority of the variance in these incredibly massive models was captured in just 16 or fewer principal directions. No matter what they are learning, they compress down into the exact same mathematical architecture.
Section 5, the grand synthesis. And this brilliantly illustrates how all these threads come together. Whether we are talking about quantum gravity using holography, machine learning using autoencoders, neuroscience utilizing CA3 pruning, or deep learning converging on a weight subspace, across every single one of these domains, a dense, high-dimensional possibility space selectively compresses into a low-rank structure that preserves the essential function. It turns out the universe really loves a bottleneck.
Now, as your guide through all this, I do need to drop a quick caveat here, so we keep our science strictly grounded. Some of what we've discussed today are rigorous mathematical proofs. For instance, Zamalchikov's C theorem strictly proves a monotonic decrease of degrees of freedom. Physics literally forgets short-distance behavior, and the Math-Schwag mapping proves an exact translation between physics renormalization and machine learning models. But things like Hassabis' learnable universe, that's a provocative conjecture. And the exact match between hippocampal pruning and ML bottlenecks remains a really compelling structural analogy. The actual math for those is still being written.
But that leaves us with this breathtaking final thought to ponder. If physics constructs space-time through compression, and the biological brain constructs memory through compression, and the AI constructs understanding through compression, are intelligence and gravity just two specializations of the exact same universal rule? It completely changes how you look at the world, doesn't it? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I will see you next time.